Welcome back to the deep dive. If you need a shortcut to being instantly well-informed on a complex technical subject, you are definitely in the right place.
Today, we're tackling something that happens in, well, pretty much every programming language. The painful, but often necessary, migration of a build system.
And this time, we're in the world of Haskell. We're looking at moving a project from the older Cabal system to the more modern, more opinionated stack system.
Right, and this is the kind of technical drama that, it really defines a lot of modern development.
Our sources for this are just fantastic. We have the actual troubleshooting log from a developer who went through this exact process.
Every command, every error.
Every single frustrating version conflict, all the configuration quirks they ran into, all to get their project, which is called Fish Moved Over.
So our mission here is to really shortcut that learning curve for you. We're going to unpack these dependency conflicts so you can see the map of the minefield ahead of time.
Exactly. Understanding why Stack throws a fit over certain version numbers. That's the real goal.
And how those versions connect to things like GHC compilers and these things called snapshots, that is the win.
Before we jump into that first fateful command, let's quickly frame some of that jargon for you. When we talk about Stack, we're going to be talking about resolvers and snapshots.
And that's crucial. Stack's whole power comes from its resolver. Think of something like else 24.25.
Okay.
That resolver points to a snapshot, which is this massive, curated bundle of packages that are all guaranteed to work together.
So it's like a pre-tested environment.
Exactly.
Yeah.
It includes a very specific GHC compiler version, all its core dependencies, everything. So when you build, everyone's on the exact same page.
That sounds great in theory. It sounds like it guarantees stability.
It does.
But what happens when your project, which was started with Cabal, doesn't really care about those rules?
That's where the trouble begins.
Yeah.
And it begins with the most optimistic command in this whole story.
Stack in it.
It fails. Immediately. Right away. It hits this conceptual wall. The whole idea of stack init is it's supposed to read your existing .cabal file and create the new stack configuration from it.
But it can't even do that.
It doesn't even get past the front door.
The error is error. S242, unable to parse Cabal file. Unsupported Cabal version 3.14. Let's just pause on that. This isn't a library problem.
No, it's a tool reading problem. It's a classic case of the ecosystem just moving a little faster than the tool itself.
Oh.
The project was using a modern Cabal spec, version 3.14.
And Stack was, what, behind?
The version of Stack they were running only supported specs up to version 3.8, so it's an immediate, jarring conflict.
And this is where it gets really interesting, because the tool's advice was actively misleading.
The error message explicitly said, recommended action, upgrade your build tool.
So the developer, doing exactly what they're told, runs Stack upgrade.
And gets the message, current Stack version, 3.7.1, available download version, 3.7.1.
So you are already running the most recent version.
Exactly. The tool tells them to upgrade, and then immediately tells them they can't. It's a catch-22.
I mean, doesn't that sort of undermine the whole promise of Stack being this modern solution if the latest version can't even handle a common, newer file format?
It's a really valid question about, tool lifecycle management. Stack is phenomenal at dependency resolution, but its ability to keep up with the metadata standards like the Cabal spec, that seems to lag a bit.
So it forces the user into a corner.
Right. You either change your project just to satisfy the new tool, or, well, there is no or in this case.
So what were the actual paths forward?
Well, the notes show two. The one they eventually took was manually downgrading the Cabal spec version in their .cabal file, just changing 3.14 to 3.8.
And the other option?
Was switching to a more volatile nightly build of Stack, but that completely defeats the purpose of moving to Stack for its stability. So they stuck with the LTS path.
Okay, so we know the fix is coming. But before they even apply it, the developer takes this little detour to clean up their environment.
Yeah, and this is a great little knowledge nugget. They kept getting this persistent Nix warning.
Ah, Nix, another package manager.
Right. They had Nix version 2.26.3 specifically on their system path, and Stack saw it. So it kept printing this warning. Warning, Nix is on the path. But Stack's Nix integration is disabled.
So why does Stack even care, and why is the integration disabled by default?
Stack wants to be the king of its own castle. It wants to manage its environment completely. If you enable Nix integration, Stack starts delegating things like system libraries to Nix, and that changes its whole deterministic behavior.
So it's a philosophical thing, keep the build self-contained.
Exactly. The warning isn't critical, it's just noise. It's annoying.
So how'd they fix it?
pretty elegantly.
Yeah.
They found the global stack config file with stack path global config and just added one line, notify if nix on path.false.
Done. Silent and solved. Okay, so from nix noise to stack's own internal baggage, the developer runs snapshots.
And this is where we see a bit of a rough edge on stack. The command spits out these really cryptic hex hashes, 2 of them, starting with B46 and D000.
And what are those?
They're cached environments. But that's all stack tells you. There's no context on what's actually inside them.
So the fact that they had to go digging through the file system themselves, that seems like a real hurdle.
It's a limitation, for sure. Stack is great at creating these environments, but not so great at helping you manage the cache. So they had to manually go into the stack root path.
And just look around?
Basically, yeah. And what they found was surprising. Both of those cryptic hashes pointed to directories containing the exact same GHC compiler version, 9.1013.
Wait, so it had 2 massive redundant compiler environments cached, taking up disk space, and no way to tell them apart or clean them up automatically.
That's it. And you can imagine this on a CI server with limited disk space. It becomes a real problem. It shows that Stack, for all its power, kind of leaves the cleanup phase to you. You have to manually prune those folders.
Okay, so with the environment now a bit tidier, they get back to the main event.
Right, back to the migration. They choose the stable path, running Stack, and iter resolve roles.
And this should be it. This should be the final successful step.
It was not. They hit hurdle number 2, and this is probably the most important conceptual piece of this whole deep dive.
What was the error this time?
Stack selected the snapshot LITS 24.25, but then immediately errored out with error. S6395 snapshot LS 24.25 does not have a matching compiler. GHC 9.10.0.3 cannot be used.
Okay, hold on. Why is that specific LTS snapshot suddenly incompatible with that specific GHC version? I thought the snapshot included the GHC version.
It does, but this is where the base package comes in. This is the iron triangle of Haskell.
Yeah.
The GHC version, the LTS snapshot, and the base package.
And the error message pointed to that.
It did. It specifically called out the project's own package, fish, and its requirements for the core base package. The project demanded base version 4.21.0.0.
Okay.
But the base version that's tied to GHC 9.10.333, the one in the environment, was only 4.21.2.0, a mismatch.
Let's try an analogy here. If the LTS snapshot is a specific car model, say a 2023 model, and GHC is the engine for that model, the base package is like the engine block's core design.
That's a perfect analogy.
And your project is demanding a part, like a fuel injector, from the 2024 model. It's just not going to fit on the 2023 engine block.
That is the perfect distinction. The GHC version is intrinsically tied to the version of the base library it provides. The LTS snapshot just guarantees a stable combination of a GHC and its corresponding base. The project was just asking for something newer than what the stable snapshot provided.
And this led to another common frustration, right? They tried to check which base version was available in the LTS.
Yeah, they tried to list it like any other package, but that fails. Because base isn't a normal library you can just install or query.
It's part of the compiler itself.
It's the DNA of the GHC compiler. You can't ask the resolver for a version of base like you would, say, base compat or some other package. The base version is defined by the compiler that the snapshot uses.
So the fix wasn't finding a new snapshot. It was changing the project's expectations.
Exactly. The developer had to go back into their .cabal file and update the base package requirement. They had to loader it to match what was actually provided by the stable alts 24.25 snapshot.
Once that dependency constraint was finally met.
The final command, stack init resolver alts, it executed successfully.
And the result is the stack.yaml file, the project's new anchor. The fight was finally over.
And once that config was written, they confirmed everything worked. They ran stack build and stack run.
Which is critical, right? A config file is useless if the program doesn't actually build and run.
Totally. But it worked. And now we can look at the actual footprint of this migration. Checking git status shows exactly what changed.
So what were the key files?
First, the fish.cabal file was modified. It had to be edited twice, remember?
Right. Once to downgrade the Cabal spec version itself, and again for that base package requirement.
Yep. And then you see the new stack artifact.
The main one being stack.yaml, which defines the resolver and all the project settings. And what about the lock file?
Stack.yaml.lock. That's where stack deterministic power really comes from. It's a generated file that pins down the exact version and even the download location of every single dependency.
So 6 months from now, on a new machine, you get the exact same build.
The exact same build. It prevents all those subtle works on my machine problems that Cabal sometimes had.
And finally, the big one, the stack work directory.
The beast, yeah. If you're coming from Cabal, this is basically the same idea as the old dist-new style folder. It's the local workspace.
It contains everything.
Everything. All the intermediate files, the build artifacts, the final binaries. If you look inside, you see this very specific structure. The dist folder, the GHC version folder 9.9.0.3 inside that.
And all the compiled output.
All of it. The object files, the archive files, and even a little local dependency database, stack.sqi3.
So that directory is really the physical proof that all that troubleshooting worked. It found the right GHC, it solved the base issue, it compiled the code.
And the project is now stable under a modern stack workflow.
And that stability, it didn't come from just one magic command. It came from actually understanding the constraints.
That's it. It's about that einen relationship between the compiler, the LTS snapshot, and the project's core library requirements.
If we zoom out a bit, this whole journey really illustrates a crucial point about any modern package manager, whether it's Stack or Poetry in Python or Cargo in Rust. The tools are great at automating downloads and compilation, but they absolutely do not automate conflict resolution.
No, the bottleneck is always your knowledge. Your ability to read a confusing error message and understand the configuration files.
It really shows that even with the most robust tools, sometimes you just have to get your hands dirty, dive into cryptic hashes and manually edit text files.
It keeps us honest about what automation really gives us.
So what does this all mean for you, the listener? Well, you now have a pretty clear roadmap for the most common versioning traps in a Haskell migration.
You've got the commands to silence those warnings, and, more importantly, the mental model for debugging that critical relationship between GHC, LTS, and base.
Which brings us to a final thought. We spent a good bit of time on the manual effort needed to figure out those cryptic snapshot hashes, and the fact that Stack has no automated way to prune them.
Right, and at the same time, we know powerful system tools like Nix are out there and are fantastic at handling environmental cleanup and deduplication.
So the question to mull over is, should future build tools focus less on managing their own, often redundant local caches?
And more on providing seamless, transparent integration with those system package managers to just solve the cleanup problem automatically.
Something for you to think about until our next deep dive.
We'll catch you next time.